Hello, everybody. So as you can see, the room's a little full. We'll talk a little bit about that later. But if everybody breathes, say, 30% less than you normally do, we'll still have oxygen by the end of the lecture. I'm John Kubitowicz, and I will be talking about operating systems. So if you thought you were going to talk about something else, you can run screaming out of the room. But do that really quickly. OK, so who am I? So I mentioned my name is John Kubitowicz. Most people call me Professor Kubi because they can't pronounce my last name. That's OK. Actually, I was in Eastern Europe a few years ago, and everybody was pronouncing it Kubiatovic or something like that, which is probably more correct in some distant past. But I'm fourth generation, so Kubitowicz or Kubi is fine. I have a background in hardware design. So when I was at MIT, I actually designed parallel processors. One of them that I worked on was the Alewife machine. And there's a picture of the communication and memory management unit that we actually built. I also have background in operating systems, I guess you would hope. I worked for Project Athena at MIT for a while. We were one of the first organizations to actually build distributed systems where you could sit at any workstation and your files were available. Now, I know that seems pretty odd to you guys now, but that was a big deal back then. I was a device driver developer, worked on early versions of the network file system. I also did some high availability work for a company called Clam. And I'm also the head PI in the PAR lab on their new operating systems effort for Minicore, and I'll talk about that later in the term. There's a picture of our logo for tessellation. That's our new operating system. I also did a lot of work on peer-to-peer. So when I first got here 12 years ago or whatever, my biggest project was called Ocean Store. And there we were kind of interested in preserving digital data for the very long term, like 1,000 years, and then making it widely available. And we're getting closer to that, although those of you who like to store your photos online may get rudely awakened someday to find out that all your photos that you thought were safe got killed off by a system error. So I don't know that we're actually there yet. But and then finally, I also do research in quantum computing, which probably is the least relevant thing to this class. But I'll be happy to talk to people if they're curious offline about that. So our goals for today, what are the goals for a first lecture is usually something like, well, here's the topic, here I am, here's how the course works. Hopefully you like it enough to stick around, although maybe I want to scare off enough people so the room fits. I don't know, we'll see. I'm just kidding. But today we're going to start by talking about what's an operating system and what is it not. We'll give some examples of operating systems design. We'll talk a little bit about why maybe studying in operating systems are a good idea. And again, say a bit about how the class operates. And interactivity is important, so feel free to ask me questions. OK, so somebody ask a question. Come on. You can do it. Yes?
How long did it take you to grow that mustache?
Well, not very long. I have to keep trimming it. Another question. Yes? We're going to stick with this room. So, and the reason we're going to stick with this room is because it has the Screencast, which gives us webcast. So I will talk more about the fact that we're oversubscribed a little bit later. There was another question. Yes?
Did you get your Sprint bill fixed?
Yes, I did. Thank you very much. So, why is this fun? So I'm a systems person. I don't really consider myself operating systems. I don't consider myself a hardware person. I design or networking person. I design systems. And the heart of the reason systems design is so fun is this thing called Moore's Law, which you've probably all heard about. But let me reiterate a little bit. It basically says that the number of transistors on a chip has been doubling every, say, 18 months for a long time. Okay, and that's pretty amazing when you think about it. In the course of, let's take the easy thing, 6 years, that says what? You've gone up a factor of 16 in number of transistors. So you can do a lot when your resources keep growing. Okay, and this, by the way, is Moore's Law. Moore's Law is not about performance. Okay, that's a confusion which I will try to get rid of in a couple of slides here. And in case you hadn't noticed, the world right now is a huge parallel computer. Okay, at the high end, we've got big servers. We've got Googles, we've got Amazons, we've got all sorts of huge server farms out there, and on down to lots of little devices down at the bottom end. So for instance, at Berkeley here, people are looking at the little devices made out of silicon that move, okay? And everything in between. Here's a picture of a car I purchased a few years ago. How many processors are in a typical car these days? Does anybody know? Yes? 100? Yeah, 50 to 100, yeah. Believe it or not, that's a lot, right? That means your car is a parallel system, and you hope it doesn't crash too often, right? Here's my new phone, right? This is the Evo. That is very definitely tied into the world parallel system, as are probably every other phone you guys have, yeah. So this is so there is some move afoot to restructure 162-bit. This is the original version of it. So, but obviously I put in new material every year. So 6 and 1, 6.5 of one, half a baker's dozen of the other. So basically, what I want you to know is, to start with, the world is based this huge parallel system with lots of components somehow interacting together, and often doing so in a way that does what you want, okay, and sometimes not. And this class is really about what structure can we put onto a system like this to help it perform more than often the way you expect. Okay? Now there's this other trend, by the way, which is kind of fun. David Culler talked about the people to computer ratio over time. So this is a log. Oh, by the way, on Moore's Law, these are always linear on the time axis and log on the number of transistors axis, and it's a straight line. Okay, so that means it's exponential. This is another case where it's linear on the year axis and log number of people per computer, and that's been rapidly going down. So basically, whereas in the beginning there might be one computer and many people for that one computer, now you've got 100 computers in your car, you got one in your cell phone, or your 2 cell phones, or your 5 cell phones, you got an iPod. You know, the number of CPUs that you've got personally is large. It's a different era that we're in, and it's the one that you're all used to, right? Because this is where you grew up. Now, this is what people typically called Moore's Law, and this is actually Joy's Law, for Bill Joy. And what it says is that the performance of computers has been doubling roughly every 18 months or so, up until about 2003. Does anybody know what happened in 2003? Or 2002, somewhere in there? Yes? So the question is, did the transistors get so small that... So it turns out that, believe it or not, Moore's Law is still continuing. So transistors are still going for a few generations. But somebody said power wall. Yeah, so one of the biggest problems is somewhere around here, it got to the point where you couldn't improve performance anymore without increasing the power drastically, which means if you got a laptop, you're burning your lap, right? If you've got a battery-powered device, it's draining out in a few moments. Okay, and so the power wall was a really big problem here, and there are other ones, which is, for instance, this performance improvement depended on being able to extract parallelism automatically from software without telling the programmer about it. And that's something that if you took 152, you'd learn a lot about. Okay, but we're not going to talk about that in this class. The bottom line, though, is that this performance has fallen off. So if you had a programmer who was lazy, which was basically most of them, it's nothing against programmers, right? Was basically said, well, my program's too slow now. If I wait 18 months, it'll be fine because the computer's twice as fast. Okay? That doesn't work anymore. So now what? Well, I guess we put multiple processors on a chip, okay? You probably cannot buy a laptop or a netbook or a desktop computer these days without talking about how many cores are in it. Does it have 2 cores? Does it have 4 cores? 6 cores? Okay, they're off onto some weird non-power of 2 thing, which is always a little jarring, like 12 cores. Okay, that's enough to screw you up for days, right? But anyway, the point is that they've given up trying to make individual processors faster, and now it's all about more processors. And so that makes the complexity higher, even down at the lowest level. Okay, so it won't be all that long before the cell phone you're carrying has multiple processors on it, and then how does it work? Does it crash all the time? Okay. So back in 2007, here was a test chip from Intel that actually had 80 processors on it. You've probably, how many people have heard of that one before? Anybody? A couple of you. There's a new one that they call the single cloud computer that just came out. This has only 48 processors on it, but it's got a lot more interesting stuff for them to talk to each other. So it's got an actual mesh network. It's got lots of memory bandwidth, hardware support for message passing. So this one is much more like an actual parallel computer, where this one was kind of a demonstration of concept. Yeah, we can put a bunch of processors on a chip. So many-core is a term I'll probably throw around. We like to talk about it in the Par Lab all the time. And what does it mean? Well, you probably, if you look in the industry, you see multi-core. But if I say many-core, what am I saying? Well, 64 processors, 128. Hard to say exactly, but let's say 64. So we're talking about a lot of processors as a target for where the industry's going. It's kind of interesting. So what do you do with a 64 or an 80 processor thing? Well, you have 2 CPUs for the video and the audio. You got one for your word processor, one for the browser, and 76 of them are doing virus checking. Okay. Now, yeah, that's probably not a particularly good use of resources, but it's the one that's kind of obvious, right? And I would say what's interesting about this is now that parallel computer that is the world that I mentioned earlier, we've got to figure out how to do parallelism at the lowest level. It used to be it's very easy for Google to use hundreds of thousands of processors. Why? Because hundreds of thousands of people every second are asking them to do things, and each one can be an individual processor. Not a big deal. Okay, parallelism by independent activity. When you get down to the lowest level, it's trickier, and you've got to actually take your PowerPoint or whatever it is you're doing and divide it up in parallel. Much trickier. Okay. Any questions on that? So we're in a kind of a brave new world here where Intel and Microsoft and all of those are not entirely sure what they're going to do with all these processors. Okay, but they're basically producing them anyway. So here's another power challenge. Somebody said the power wall earlier, which was great. Here's a funny thing. If you were to actually take and go on Moore's law curve of transistors and just use all those transistors, what you'd find is that, remember, everything's getting smaller and there's more and more of them on a little tiny chip. If you were to actually follow and use all those transistors, you very rapidly get into the regime where your power density is something like a rocket nozzle. Okay, and I don't know about you, but I don't want that while I'm sitting with my laptop on my lap. Okay, seems kind of unfortunate. So this is exactly the power problem. Okay, if you put all those transistors on a chip, you can't afford to use them all because they're all burning power or they're using up your battery. Either of those are not desirable. Okay, so this is where we're at. Okay, parallelism. So we're now in the world where parallelism is everywhere, and part of this is what we're going to be trying to deal with in this class. Although we're going to start out with a serial view of the world, we're going to move into parallelism fairly rapidly. Okay, at least we're going to start with serial view, then we're going to move into a concurrent view, where in theory things could be moving in parallel or not, and then we'll get into a parallel view. Of course, this is about operating systems, so we're going to spend some time talking about the organization of the operating system. That's what this class is about. So here you might say is a typical interior of some computer. This is a picture right out of your book. And what you see here is that there's a CPU, but then there's also all of this other stuff, right? There are disk controllers that talk to disks. There's sort of a USB controller which talks to a whole bunch of things, printers and keyboards and mice. There's graphics adapters, etc. So the interesting part about the computer is not just the processor. Okay, there's a lot of other interesting stuff. There's the I/O. Okay, and if you take a computer processor-oriented class like 152, sometimes, depending on who's teaching it, you might get the impression that all that matters is the CPU. Okay, fortunately, in this class, we know better because we have to deal with I/O, and that's going to be something we talk a lot about. Okay? And for instance, this is an older chipset now, but the Pentium 4 chipset, what's kind of interesting is you take a diagram from Intel, and here's the processor up here, and then all of this other stuff. Okay, so there's typically what's called the north and south bridges, and the north bridge is handling a bunch of memory and the graphics controller, and then the south bridge is handling a bunch of other things like audio and USB and flash and networking and all that's disk drives, etc. So again, the complexity of the I/O is kind of an interesting thing. Okay, now the way I view complexity in this class is it's something that you can't avoid, and the better thing to do is to tame it. Okay, so I'm trying to point out that there is some interesting complexity that you get just because you're dealing with computer systems, and it's really a question of can you tame it in a way that gives you, what did we say, what you would expect it to do most of the time. Okay, now ideally you'd like it to do what you expect it to do all of the time. That's a pretty tall order. So if you were to actually take, so I used to teach 152. I've also been known to teach 252. I do that pretty regularly these days. There's a lot of topics in computer architecture. We talk about what's inside the processor. There's a lot of issues there. We talk about the networking side. We talk about storage side, the various sorts, memory hierarchies, etc. All of these, in theory, are levels of complexity the operating system may need to deal with. Now, we'll touch on a lot of these things just because we have to as part of the topic of this class. Okay, but if you were to actually be interested in the hardware aspects of this, you'd probably take a 152 or a 252. Okay. This I find kind of an interesting statistic here. Here's the increasing software complexity. So if you look down here, we've got sort of number of lines, millions of lines of source code, and you can see the space shuttle right here. And then you see Vista there, and I should really try to get an updated version with Windows 7. But kind of interesting. What do you see? You see trend up, okay, complexity. You wonder why it is that modern operating systems give you the blue screen and crash all the time. Okay, I suspect it has something to do with number of lines of code. Okay, and as much as one likes to maybe make fun of Microsoft sometimes, or even Apple sometimes, some of it is not really their fault. It's because everything is so complicated. And complexity breeds faults. Okay, now that isn't to say that I'm not going to make fun of said organizations. I like to do that over time. But just realize that the more complicated thing you're trying to do, the more chance there is of being failure involved in it. And then it's all about how do you structure your code to have the least likelihood of failure. I sound almost like a software engineering pundit here. You know, it's all about the organization of the software. It's all about how you engineer it. But in fact, that's true. Okay, because this is 60 or 50 million lines of code is a lot of millions of lines of code. Okay? I don't know, how many of you have written 50 million lines of code? Anybody? Bueller? Sorry, that's an old reference. So let's suppose, for instance, we were interested in, say, a Martian rover. Okay, now there was, the Pathfinder was one of the Martian rovers that actually did reasonably well. And Pathfinder, because it was going to Mars, had some hardware limitations. Now, what's kind of nice is if you stay on Earth, you sort of get the latest stuff, and you're maybe not as limited. But let's look into this for a moment. There was now I know this is hard to believe, a 20 megahertz processor. Okay, yeah, that's M. Okay, 128 megabytes of DRAM. Okay. VxWorks operating system, which is a real-time operating system. It had a payload with cameras and instruments of various sorts and batteries and solar panels and obviously locomotion equipment so it could drive around. Lots of independent things all worked together. So it's driving itself around on Mars. It's avoiding craters and rocks. It's somehow positioning the antenna so that it's actually able to receive commands from Earth. What have you, and all of these different things need to be going on simultaneously without them crashing each other. Okay, and because when it's on Mars, it's not like you can fix it. You can put in a service call, right? Can't hit the reset button. All right, so that actually is kind of an interesting challenge in itself. It says kind of that you got to make sure to be able to hit the reset button remotely, if possible. Okay, so that Control-Alt-Delete, right? Somehow you got to be able to send that command. Of course, you want to hope that the aliens aren't sending that command too often. But it always needs, among other things, to receive commands from Earth. Okay, and individual programs can't interfere with each other. Was there a question back there? No. So, for instance, you got the Martian Universal Translator module, which is hoping to communicate with the natives. And it better not screw up the antenna positioning software. Okay, and those two things, hopefully, as the programmers and the program teams involved could think about them separately without worrying about how they interact. Okay, think about how bad it is. You have enough trouble trying to make sure that this thing can avoid rocks. And the guy who's trying to avoid rocks has got to worry about whether the translator unit is going to crash at the wrong time. Okay, that you just couldn't do that. So in order to make something like this work well, you really need to engineer it carefully. Okay? And of course, all software crashes. All right? It doesn't matter how good you are. And of course, the key thing there is make sure that a crash doesn't screw you up too much. Okay? So this is all about fault containment, which is an interesting topic that you probably haven't heard a lot about up till now. And it's how can I make sure that when something does fail, it doesn't propagate its failure onto other parts of the system. Okay? And, of course, the other thing is certain functions are time critical. How many of you have been listening to music on your PC and you went to pull a window up and the first thing that happened was you heard a glitch in the audio and then the window came up? Anybody experience that? Or you're looking at a video and you go to do something else and the video glitches. Why is that? Why does that happen? Anybody? What about concurrency issues? Okay, so something about the way they work together. Let's. There's another person with their hand up. Anybody want to add to that? Yeah.
The network might be overloaded, so it might not be losing packets.
Yeah. Okay. So if there's if there's a network somewhere, there might be overloaded as a result of what you're doing. Right. Let me ask you this. Let's take the audio example specifically. Do you think that playing, I don't know, Taylor Swift requires a lot of CPU or network? How many people think, you can insert somebody else if you like. How many people think that playing an audio requires a lot of either CPU or networking? Anybody? How many people aren't sure? That's okay to be not sure. Okay. How many people think that it doesn't? Okay. So it turns out that playing audio really doesn't require anything in resources relative to modern machines. They're so fast. The reason you get a glitch is because even that little bit that they need get taken away by a bad scheduler. Okay? That, I would say, is kind of a bug. It means the system doesn't respond well to real-time tasks. I will tell you that a Martian rover better handle real-time well, because if it's about to try to avoid going off a cliff and there's a glitch like we were talking about with the audio, it's going off the cliff. Okay? So the reason I bring up this Pathfinder example is it kind of illustrates some of what we want to make sure to understand here. If you're going to design a system, you got to sit down and know what the requirements are, and then as part of knowing the requirements, you want to know how the pieces interact with each other and how to avoid unintended consequences of those interactions. Okay, and that's what this class is about. How to avoid unintended interactions. So how do we tame this complexity? Well, just to throw more complexity at you, every piece of computer hardware is different. You have different CPUs, Pentium, PowerPC, Coldfire, ARM, MIPS, you name it, or there are different generations of those CPUs, whatever. You have different amounts of memory, of disks. You have different types of devices like mice, keyboard, sensors, cameras, fingerprint readers, whatever. You've got different networking environments with firewalls and TCP/IP or some sort of wireless, whatever. Lots of complexity. If you're a programmer, should you have to worry about every different computer your program might run on? How many people think that might be bad? Okay. Yeah, that would be very bad, right? You guys understand permutations. Come up with how many permutations of possible computers there are, and imagine writing one program for every permutation. You'd go blue in the face, right? That'd be awful. So somehow we've got to fix this problem, okay? And this is all part of the same complexity problem. So the first question was, does the programmer need to write a single program that performs many independent activities together? Okay, well, you got the guy worrying about navigation, the other guy worrying about translating Martian speech. Those two shouldn't have to worry about each other. Okay? And then does every piece of, do you have to alter every program for every piece of hardware? Hopefully no. And does a faulty program crash everything? Okay, so hopefully the answer is no to all of these questions, and that's part of what we want to do in this class. Okay. Question in the back? No. Stretching. Okay, good. So, and then there's, of course, this other question of, does every program have access to every piece of hardware? So why should the answer to that be no? So who said security? Okay, why? What about security?
Well, theoretically, a program that you download on your computer that have access to hardware could start messing around with all your hardware, taking up all its use instead of letting it use it.
Okay, so one key problem, so you talked about what I'd call a denial of service attack, which is that if one program can use up all the hardware, then it could prevent another one from using it. Okay, what other types of security problems? Yeah?
Root access to the hard drive.
Yeah, so what do you mean by root access to the hard drive?
You don't want them to be able to read files they don't have permissions to.
Okay, right, so if you have multiple different people with data on the same computer and you have a program that has access to the disk drive without any intervention of the operating system, they can get all that data. Doesn't matter if they own it or not. Yeah, what else?
Certain programs don't need access to certain pieces of hardware. You don't even give chess access to like the printer.
Okay, so certain programs don't need access to other pieces of hardware. Okay, I'll buy that. So why is that a useful thing then to deny?
You don't want them to accidentally crash.
Good. Good. So did everybody hear that? So one reason we may want to prevent other people from using all of the hardware is just because if by accident they might screw the hardware up. By putting firewalls, and I'm going to use that term loosely, around your program, you make sure that it doesn't have any unintended consequences. Okay, there was another person. Anybody else? Okay. So there's this general notion of virtual machines. They talk about this in your book, and we're going to sort of use it as a way of thinking throughout the term. And this is a rough diagram of what I mean by this. And at the bottom, we have all of our hardware. Okay, this is your memory, your processors, your disks, your networking, whatever. On top of it, we have the operating system, and then up above that, we have the application. Okay, now this line here is what I'd call the physical machine interface, because the operating system is basically working on top of the hardware directly in most cases. Not always. We'll talk about that in a moment. And then the operating system presents a new interface to the applications. That new interface is one that's been virtualized. It's the firewall that we draw around the application and give it kind of a rose-colored view of the hardware. Okay, we're not going to allow the application to have access to all pieces of hardware. And the other thing is hardware is kind of limited in many cases. So a simple example is you take a network. Okay, the Ethernet protocol, we'll talk a lot about that later in the term, takes packets, but those packets can get lost. They're small, okay, et cetera, et cetera. They don't, a single segment doesn't get you from here to China. And so what we want to do is put on top of that a much better interface, say TCP/IP, that allows you to have an abstraction of a stream, which you open a socket on another machine in China, and you send bytes, and they all make it there. Much better interface. Okay, so hardware's limited, and we want to fix it. So this is all about virtualizing. Now, so you could say that we're, again, software engineering, right? We're turning hardware-software quirks, okay, which is some combination of hardware and something maybe a little bit into the operating system, into something the application user wants. Okay? And we're going to optimize for convenience and utilization and security and reliability and all of these things. This interface is going to be a much more stable interface, hopefully, than the hardware. Okay? And for any operating systems area, you pick one, file systems, virtual memory, networking, scheduling, whatever. You ask yourself, A, what's the hardware interface? B, what's the application interface? You compare those two, you have a good idea what's going on in between. Okay, and so a lot about what we're going to be talking about this term is how to get from here to here. And do so while getting all of these kind of nice properties. Now, this is one of my favorite slides that Patterson put together. Okay, how many people have ever had a class with Dave Patterson? Okay, if you ever get a chance, you should definitely take a class with him because he's a lot of fun. But this is the instruction set interface, okay, which was stable for 20 years. And this is basically, he likes to say this is Microsoft dancing on Intel. But this is a good example of a stable interface, in this case a hardware interface, that was put together and basically stayed there long enough for software folks to be able to rely on it. Okay? And so in many cases, these interfaces here are all things that are stable over time that somebody's put together in a way that the applications can rely on them. Okay? And, you know, there's lots of classes in Berkeley here about interfaces, right? And the funny thing about interfaces is in many cases they're historical. Okay, I hate to tell you this, but sometimes engineering elegance is not the reason the interface is that way. Okay, it's kind of like you go to a city that wasn't go to a city in Europe. Okay, is it nicely ordered with concentric circles or grids? Probably not. All right. Sometimes you can see cities in the US that were engineered from the beginning and they're nice grid-like or nice concentric circles, but that's rare, right? And unfortunately, you take a city like that that's beautifully laid out, and then when they put the suburbs in, it's just a mess, right? So interfaces are as much about history as they are about engineering. So there are some times where we'll talk about interfaces and there'll be some quirks, and we'll have to talk about the quirks. But for instance, 152 is about the machine interface. 160 is about human interfaces. 169 is about human interfaces to big projects. Good class, by the way. And you can ask questions about, should you ever move something from one interface to another? So for instance, just to go back to our example here, maybe you find that a certain interface here is extremely useful, but also slow because there's a lot of layers of software. What could I do? Well, maybe I could actually migrate some of this down into the hardware, and then the amount of software between here and the application is a lot smaller. Okay? Good. So what's a virtual machine? So it's a software emulation of some abstract machine. Makes it look like the hardware's got the features you like. Take TCP/IP, I said earlier. You make it look like the hardware's got this great network queue interface that reliably sends bytes to China. Okay? And one of the advantages of virtual machines, which I'm just going to briefly mention, is it also sometimes allows you to run programs that it thought they had one piece of hardware on different hardware. How many people have heard of VMware? Okay, good. This is the company that made their mark doing that. And virtual machines give you simplicity. This is just restating what I said. Every process thinks it has all of the memory and CPU. Does it? No. The virtual machine mediates. But it can pretend it's got them all. It can pretend like it owns all the devices. Does it actually? Well, no. It tries to go to a device it doesn't have access to. It is prevented. Or more subtle is take our networking example with a video that we want to make sure always plays no matter what. We could actually give access to the network from some other device, but make sure that it never uses too much network to screw up the video. Right? So we can actually talk about quality of service. Virtual machines can give you fault isolation, okay? Because if the thing screws up the virtual hardware, that's okay because it's virtual. Okay? And finally, it can give you protection and portability. So for instance, Java, which you're probably you guys hopefully all love and adore because you'll definitely love and adore it by the end of the term if you don't. It's a good example of a virtual machine implementation where the Java program runs inside of a sandbox that then runs on the real hardware. Okay, so Java itself is actually a virtual machine. Okay, and here's an example of what you could get with VMware, for instance. So here's hardware. You've actually got, say, the Linux operating system. That's just one possibility here. And then VMware provides a virtualization layer, and then I can actually boot BSD and Windows NT and Windows XT and Windows 7 and all that sort of stuff, each in their own little container on top of VMware. And they can all be running simultaneously, and each one of these operating systems thinks it has complete access to the hardware. Okay? So this is kind of the ultimate example of fooling the application, which is now actually an operating system, into thinking it's got the whole level of hardware. Okay? Everybody see how you can recurse this as much as you like, although nobody ever goes more than 2 levels. Okay. Cursing and recursing. So, okay, so if anybody has any more questions about virtual machines, then I'm going to talk about the class. So, questions? Okay. Anybody here have a laptop with VMware running on it? Just out of curiosity. A few of you. You probably do that to run more than one operating system at the same time? Yes? Okay. Good use. All right. So let's talk about the course. I'm John Kubitowicz. As I mentioned, I am in 673 Soda Hall. Some of the time, I'm actually in the Par Lab the other times. And that's on the 5th floor of the Soda Hall. I have some tentative office hours, which I put together Monday, Wednesday, 2:30 to 3:30, although sometimes that doesn't work out for people because they have a class during there. So just let me know, and I can move office hours around or set up special meetings, whatever. There are 3 TAs, who would I like to stand up, please? TAs. So we've got Angela. Okay. We got Christos, yeah, in the back. And we got Hilfi. Hello, everybody. Welcome. And by the way, you 3 should come down here at the end of the class so you can help hand out course forms. Okay. Labs are going to be on the 2nd floor of Soda Hall, although people can import the Nachos environment typically on their own laptops and stuff, and they do that too. There is a website which hopefully people have noticed it's been mostly updated recently, but basically my primary mirror is actually the one off of my homepage here. So if you go to www.csberkeley.edu/cs162, that's actually the original version. This one that's off of the instructional website's a mirror. Okay, so the only reason I tell you that is that sometimes you go to that instructional website and you're like, Professor Kubi said he put something up and it's not there. Try my website, because it's possible I just forgot to synchronize. Okay? But anyway, this will be your portal into the class. Everything is there. Okay, so let's take a look there for a second. So, So here's the website. There'll be announcements on there. There's some overview of the class. There's information, which will get a little more updated as time goes on. The lecture page is the key, okay, because this is the ultimate schedule. So if you're trying to figure out when things are due and whatever, go to the lecture page. I just realized I forgot again to make the nachos page up to date. We'll fix that. But if you're ever wondering whether a date is such and so, always go to the lecture page because I will put assignments on here and so on. Okay? And this will also show you topics. I'll try to get slides up early, but even if I don't, the ones that are in italics are actually from the last term, so you can kind of see roughly what I'm talking about. There'll also be readings in either the 8th or 7th edition of the book. I'll talk about that in a second, sometimes even the 6th. And sometimes there's also interesting links here that are readings. So here's a Turing Award lecture from Corbato on building systems that will fail, talking about a very interesting, extremely complicated project that we'll talk about later. Okay? So that's the website. To know it is to love it. And what else? There's also a news group, which the TAs will be reading. Oh, webcast. Hopefully, this class is webcast. Now, what do I mean by that? Well, it's actually, you see there's no cameras that are visible here. This is actually what's called screencast, which means that they take the capture from my laptop and my mic, and they put it together into a video that goes up, that I'll put up on the website. That will also be available within a day or two of the class. So this is not a live webcast. It's sort of a delayed webcast. The unfortunate thing is, since there are no humans involved, sometimes it doesn't capture. So for instance, if I plug my laptop in slightly later than 9 after the hour, then it doesn't always guarantee to capture the video, things like that. So hopefully we won't have too many instances of that, but sometimes it happens. People find the webcast to be very useful. There's a news group the TAs will be reading from, okay, UCB class CS 162. Course email, okay, this is a way to get a hold of the TAs and so on if you have problems. There's going to be a reader, which is not quite ready yet, but it'll be down at Copy Central on Hearst. How many people know where that is? You know where that is, right? So the reader, people ask me, is the reader required? Well, nothing's required, but I highly recommend it. What it is it's a copy of all of my slides and the source code for nachos that you guys will need. And so it's very useful to be able to carry that around rather than trying to print out stuff, okay, and using up the Amazon rainforest. So we will tell you as soon as the reader is ready. Okay, schedule. Class time, as you're well aware, is 4 to 5:30, or according to the clock in the back, it's 20 to 8 to 20 to 8. And make sure to come to class, even though there is a webcast. What you see here is there's a lot of good interaction and good questions and answers. And so much better if people are here. I find that while people can get a lot of information out of the webcast, it sort of gives you a disconnected view of the class. So I'm a big fan of actual people being in person. And 10% of the grade is actually from class participation. So your TAs over time are going to get to know who you are. They know who you are. And so they'll know whether you're participating. This will be in section as well. Okay, so make sure to come and participate. So sections are important for this class, okay, because we actually give information in sections that may not have been fully covered in class, or we may expand on things. So go there. Now, telebears. All right. How many people weren't able to get into a section in telebears? Do we have anybody? Okay. So there are now 5 sections. There used to be, I'll show you them in a moment. Yes, there used to be 4, but there are now 5. And your telebears assignments are completely irrelevant in the grand scheme, except for Friday, this Friday. Okay, so you should all go to the one that you were assigned by Telebears this Friday. Hopefully by next Friday, the following one, we will have given you your new sections. And the idea of the new sections is that everybody who is in your project group has to attend the same section. Okay, and this is a requirement because the TAs, first of all, need to be able to interact with the whole group at a time, and also for load reasons, we want to smooth things out. So we want to make sure that everybody in your group is in the same section. Now, usually we are able to make this work, but there will be a time, a little bit later this week when we'll put up the ability to sign up for sections. Don't do that quite yet. And hopefully it'll work. But very important that unless absolutely required, you sign up for 2 sections. Okay, so try to figure out which 2 sections you and your group can attend. And those of you that can only attend 1 section may have to send me good justification of why only 1 section is good. That's doable, but yeah. You mean, were there any sections last Friday? No, there are definitely sections this Friday. So whatever that is, Friday the 3rd or something, there's definitely section this Friday. Go to your Telebears section. Only this Friday. There are other questions? Yeah. No. Yes, you have to attend 2 sections a week. No. Put it this way. We are going to do a massive on-the-fly reassignment of sections. And if you give us 2 sections your groups can attend, it's more likely to converge. It's kind of like trying to compute the last digit of pi, which is my favorite number we'll learn a lot about. The more options we have, the better it converges. Higher terms in the series. Other questions? Now let's talk a little bit about the wait list. How many people in here are on the wait list? Okay. So here's the story. I don't know what it is about this term, but we had 200 people that wanted in this class. That's a lot. As of last week at some point, I believe we booked this room to 110%. So if you're still on the wait list, your chances of getting off of it are vanishingly vanishing. Now, I don't want to scare you away because what typically happens every time every first week is that people came here to sit in and see what's going on, and then they drop or something. So it's not to say that you won't get in the class, but it's right now we're kind of overbooked for this room. Now, I'd love to actually have everybody in here, but the problem with moving rooms is that then we lose the webcast and things get tricky. And so, yeah, that's a problem. Now, because there are very few rooms like this one. There aren't too many people that know this, but I think in our department this may be the only one that does this trick. There may be a new one over in the Citrus building, but I'm not sure. The other thing is there is a pecking order that deals with seniors and then juniors and then concurrent enrollment folks. So you can kind of judge where you are in that scheme. But anyway, I would say wait until it shakes out a little because it always does. Okay? Don't give up hope yet. But if you're number 30 on the wait list, that's probably not good. Okay. Now, textbook. Silver Shots, 8th edition. This is a pretty good textbook. It's got a different viewpoint from mine in a lot of topics, which makes it good. It's a good thing to look at, and everybody should get a copy of it. I put readings up on the lecture page. Remember your friend? That sort of say what readings are appropriate for my given lecture, so that's useful. This actually has more modern material than the 7th edition, so I know that people who shop at Ned's and so on like to get older editions, but is Ned still around? Do they? Yeah, okay. I actually haven't been over there for a year, so I don't know. But I would say try to get the 8th if you can. I know there are still 6th editions floating around. That one's getting pretty long in the tooth, as it were. The 8th edition's been out for a couple years now, so I suspect you can even get used versions pretty easily. There are online supplements, so if you go to the information link, there's actually supplements to this. Interesting readings, appendices, some sample problems, and so on, which is useful. So I guess I answered this about the 8th edition. Our topics of coverage are going to be something like this. We're going to talk about fundamentals for the first week. We'll talk about processes and threads. Then we'll talk about synchronization and scheduling. Talk about protection, address translation, and caching. Demand paging, file systems, networking. Protection and security. Other. Last year they shortened this the term by a week to give us the RRRRRR week. The problem with that is that sort of killed off time for one of my favorite things, which is a lecture that you guys construct in the sense of by topics. You sort of say what topics you'd like to hear about, and I put together a lecture on it. And sometimes I talk about such things like, dragons is one of my topics. Or I'll talk about quantum computing. Sometimes people get me to do that. Or more on the operating systems front, talk about research topics in operating systems. Now, I do some of that for sure anyway. But what I may do, and I'll pull you guys as it gets closer, is I may have an optional lecture on the Monday of that form, which doesn't have anything to do with the final, and you can just attend for your interest, and you guys can submit topics. So would anybody be interested in doing that? Okay, well, maybe I'll do that. I mean, again, no required attendance. Think of it as studying relaxation or something. Okay. Grading. So rough grade. So another thing that happened when they removed a week is they kind of took out, I had to make a choice between material and an extra midterm. I'm not sure whether I did the right balance there or not. Usually I have 2 midterms and a final. Last fall I did only 1 midterm and a final. The nice thing about 2 midterms, I know it sounds like a pain, but it gives you one more data point on how you're doing in the class. I may poll you in a little bit to see if people would be interested in another midterm. You'd be surprised how many people raise their hand when I ask, do you want an extra midterm? It's more than you might think. But if for some reason we did 2 midterms, then this would be probably a 15-15-15 split. Right now it's a 20-25 split. There's also 4 projects, each of which is 12.5%. And then a participation which varies from somewhere between 5 and 10% depending on how things work out. Okay? 4 projects are actually working with the Nachos system, which is a virtual operating system. It's not Linux or an actual operating system. And the reason for that is the virtualness of Nachos lets you ignore things that sometimes get in the way. Like a weird pointer reference causes the interrupt controller to lock up and you sit there staring at a blank screen. Okay? These are fun kind of bugs for an advanced operating systems class. What we chose in this class was to go with a system that lets you look at the particular concepts we're trying to learn without that weirdness. Okay, now the downside of that is it's missing some of the deep device driver kind of stuff that you could imagine getting. Now, somebody earlier mentioned this restructuring of 162. One thing that may happen is I or some others may actually put together an advanced operating systems class that uses Linux and goes to the internals, which would be, this would be a prereq for that, but we'll see. Would anybody think they might be interested in a course like that if it exists? Oh, interesting. Okay. Might happen. Yeah, 162 and a half. The other thing I want to mention is this fourth project is a networking project for sure. I may actually do what they did last term. I haven't decided yet, which is a cloud computing networking thing. How many people would be interested in trying to do some cloud computing stuff? Okay. Well, that's a possibility. So the late policy. Okay, well, this is a class, which means I can't let you guys have an infinite amount of time to turn things in. Yeah, I know. Hate it when that happens. But we will give you slip days. Now, what's a slip day? Well, a slip day is a day that your group can invoke in turning in the final code of a project. Okay, and you get 5 of them throughout the term. So you're working along on project 3, and you're just not going to get the code done in time. You want to turn it in the next day, you can invoke a slip day. Okay, and you get 5 of those. Now, we've had a group or 2 in the past who have invoked all 5 slip days on project 1. I can tell you this is not clever use of your time or slip days. But the reason we put slip days in is we know that with any complex project, things happen. Okay, but you should make sure, and I'm actually going to give you half a lecture on how to interact in a group, because surprisingly few people have that right off the bat. But you should make sure that your invoking of slip days is for good reasons rather than, you didn't get started in time. Okay, but we will give you this. Now, what happens when you run out of slip days? Well, then it's 10% per day on projects. Okay? Now, there will be 2 phases to your projects, by the way. One is a design phase where you turn in a document describing the design, and a second is a final code phase where you turn in the functional code. You will be allowed to do slip days on the code, not on the design. And the reason for that is we want to make sure that you're not slipping on your design phase, because there are design reviews and everything, and that would just get screwed up. Okay? All right. Don't worry if that seems too complicated. We can repeat it multiple times. So why do we do groups? So groups are 4 to 5 members. They have to be in the same discussion section. And why do we do groups? Because the real world has groups. Okay, that's one reason. Another is these projects are sufficiently complicated that it's good to have more than one person working on them. It's good to have 4 or 5 people working on it. Now, how many people have not done a 4 or 5 person group project yet here at Berkeley? Okay. So interacting with 4 or 5 people is surprisingly complicated. When I first got here, my very first year of teaching an undergrad class, after the end of the term, I had a letter slid under my door, and I opened it up. By the way, I'm thinking, I've survived, right? I open it up. It says, "Dear Professor Kubitowitz, you have ruined my life." I'm thinking, boy, that was a bad term. So I'm reading on, and it turns out the reason that I had ruined this person's life was, quote, "I made them work with other people." Now, that is kind of unfortunate. But clearly this person did not have a good group experience. Your group experiences will vary, but hopefully won't be that bad. Okay, I do not intend to ruin anybody's life. That's probably not a good thing. You can quote me on that, by the way. But what I want you to know is dealing in groups of 4 or 5 is challenging, and you have to figure out how to work with the other people. To figure out how to adapt your schedules, how to communicate, how to organize. Okay? Believe it or not, there's a whole class, 169, which I mentioned earlier, on software engineering. Okay? We're not going to spend time going over all the material of 169, but I will give you some tips on how to deal with the groups. But just all I want you to know today is be aware that working in a group can be challenging. That's the important thing to remember. Okay? And if you know that up front, then hopefully we can avoid some of the pitfalls, and you can get help with your TA, by your TAs sort of intervening, or talk to them before there's a major problem. Okay? But I stick to the fact that groups are important. Okay? They basically mirror what the real world is like, and you're going to be engineers that go out and change the world, and so you're going to have to deal with groups. If you think 4 or 5 is a lot, you go to Intel. How many people design a processor? Well, there's 500 people that design a processor at Intel. Okay? So 4 or 5 is a small number. Of course, they actually have 12 levels of hierarchy of management to deal with it too. But so just keep in mind, communication problems are natural. You need to figure out what people have done. Sometimes I actually, when I was a grad student, my office mate had this very strange notion that all C code had to look a certain way with 4 characters worth of indentation after ifs, and that all variables had to start with a certain format depending on what functions they were in. And we were building a huge system. And the problem was he was a night owl. So what would happen is we'd all go home and, our code works, isn't this great? In the middle of the night, he'd come in and he'd work, and he'd look at the code, and it just didn't format right. And so he would reformat all of the code, change all the variable names, check it back in, and we'd come in and nothing worked. Now, I'll tell you, it's only because the windows were sealed on that 6th floor that we were on that he didn't sort of, anyway. So dealing with groups is challenging, okay? So you need to think about, how to know what other people have done, what answers you need from them, document things, keep online notebooks, whatever, okay? And we'll talk more about this. And try to communicate with your TAs if there are problems, okay? And in some sense, we actually have short progress reports, which are the design reviews that you're going to go through about what you're planning to do. And that's going to help a bit in the communication process as well. Okay, any questions about this? So let me show you my typical lecture format. This one is not typical. But so back in the early days of Soda Hall and Corey Hall, people would spend the first 10 minutes of lecture talking about administrative matters. Well, there's going to be an exam coming up next week, and you got to remember that project 4 is due here, and da-da-da-da, they go through all these things. And then they get to the material. And basically, somebody who knows a lot about how people learn came in and said, well, the attention spans are high at the beginning of class, okay, and they fall off. So basically, people were teaching administrative methods really well. So years later, you could remember when the exams were. So in light of that, my basic idea is the following. We're going to start right in with material, a little bit of a review session of the previous and real material right at the beginning. And of course, you're going to wane a little. And then we're going to take a break, which in the case of the first break is going to amount to actual administrivia. So we'll talk about things having to do with the class. Sometimes I'll give some interesting news items, etc. And of course, that'll allow your brains to recover a little bit, and then we'll be going well. And then, of course, so at that point, we'll have another break where I might actually let you guys go out and have some water, talk a bit. These are 5-minute breaks, not 20-minute breaks. So then we come back up, and of course, this is going to improve a lot. And you'll have the last bit of class. And of course, at this point, you're in kind of trouble. But watch for the keywords and in conclusion. Okay, because notice what happens with in conclusion. Wait for it. What you want to do is wait for me to summarize what happened today, that information spike, before you pack up. Okay, so when I say in conclusion, don't pack up right away. Actually, pay attention for that last few moments, and then we'll let you go. Okay, so this is basically 1-minute review, 20-minute, a couple minutes review sometimes, 20 minutes lecture, 5-minute administrative, 25-minute lecture, 5-minute break where you go out, 25-minute lecture, etc. And I'll try to get here a little bit early and stay a little bit late if you have any questions. Okay? The lecture goals interactive. I'm hoping that you guys ask me questions. Okay, that's important. I much prefer lectures with questions in them. Your computing facilities. We're going to have forums here after class is over, so everybody should make sure to come up front where there'll be TAs handing them out, but they're basically your account forms. And I don't know whether we have enough accounts, but please only take one form. Okay? And you should take this form and log in to your account, and it actually will ask you some information that you need to do right away. Okay? Things about what's your right email address. Question, yes?
Do groups get a group SVN or something?
Yes. We'll worry about SVN in a little bit, but not today, but yes. Okay? Yeah, we still use SVN. I've had questions about other things, but so try to log into your account this week. Make sure that nothing's screwed up. Take a look at the Projects and Nachos link off of the main page. Remember, the web page is your friend because that's your project information. And read the news group regularly. Okay. And of course, academic dishonesty. Yeah. So if you look at the if you actually look at the various forums and websites about this, copying all or part of another person's work or using reference material not specifically allowed are forms of cheating and will not be tolerated. Student involved in the incident of cheating will be notified by the instructor, and the following policy will apply. You can look it up. Bottom line is, do your own work, and you'll be fine. Work with your group. Okay? We actually run MOS on occasion and catch people. So try not to be using things from previous terms or other groups, okay? Because that's bad. All right? I think if you just take to the straight and narrow, you'll be fine. Okay? And people feel free to talk to me later if they want. So what I want to do, unless there's any questions about administrivia, I will finish up the lecture by just talking about a little bit of what's inside an operating system. Got about 15 minutes left or so. Any questions on course administrivia? Yeah.
How important is the recommended book?
How important is what? The recommended book, I would say try to get a copy if you can or read it in the library. I mean, it does give an important kind of alternative view to things, so it's good. If you can't afford to purchase it, there's lots of places you can go at the library, whatever, to actually read it or read it in friend. You don't necessarily have to own your own copy to get good use out of it, but I would definitely make sure I had access to it. Good. Any other questions? Yeah. There are no homeworks in this class. Sometimes I post homework that you can do optionally just to help you along to see where you're at. But pretty much it's the projects and the midterm or midterms and final. Okay. Any other questions? All right. So what does an operating system do? Well, if you read your book, an OS is similar to a government. Now, of course, this is Berkeley, so immediately we say that means an OS is bad, right? Does a government do anything useful by itself? Well, that could be another Berkeley-style question. One of the things an operating system does is a coordinator and traffic cop. It basically manages all the resources. It settles conflicting requests for resources. Prevents errors and improper use. Okay, so that's the coordinator traffic cop kind of idea. It's a facilitator. It provides facilities like the file system and the windowing system and standard libraries and so on that everybody needs. Okay, so in that sense, it's preventing you from having to deal with ones and zeros to do your Martian unit, translator. Okay. And, basically some combination of these two. So, but what is it really? Well, okay, so maybe it's the memory management piece. Maybe it's the I/O management. Maybe it's CPU scheduling. Maybe it's communication. Is email in the operating system? Okay, I see a lot of people saying no. Maybe multitasking and multi-programming, allowing more than one thing to go on. Does that belong in the operating system? How many people think that probably belongs there? Okay, I'd buy that. How about the file system? Okay. Believe it or not, you can get by without having the file system in the operating system. We may talk about that a little bit. How about multimedia support, like video? Okay, maybe video doesn't belong in the OS. Yeah, kind of like this. What about the windowing system? Okay, now it's interesting. I see some yeses and some nos. That one's a kind of a scratcher because you know, one would think that windowing is graphics and application oriented. On the other hand, Microsoft made a conscious decision about 15 years ago or so to put windowing into the operating system, which is one of the reasons it crashed all the time. But what about other user interfaces? I don't know. How about the browser? Ooh. Now, you guys are a little too young to remember this, but Microsoft was sued by Netscape and a whole bunch of others because they were claiming that Internet Explorer was a fundamental part of the operating system. Okay, and it looked like they were kind of honing in on the internet browser market and doing so kind of in a way that wasn't kosher. Okay, now it's interesting that people don't even worry about that much anymore, right? Because we have alternatives to Internet Explorer like Firefox and Safari and all these others, and it's not as much of an issue. But I'll tell you, the passions were high 15 years ago about whether the browser belonged in the operating system. And you might ask, is this only interesting to academics? I don't know, maybe. There's no universally accepted definition of what an operating system is. So everything the vendor ships when you order an operating system. Unfortunately, you buy a computer from Dell or you buy a computer from whoever your HP, whoever your vendor is, and what do you got? You got all of these preloaded apps that you never ever want to use. Right? The very first thing I do when I get a new computer is I delete everything that I didn't want. Now, you got to be careful doing that because sometimes you delete too much, but details. There is one program, and I say that kind of in quotes, that's running all the time. Typically, that's called the kernel. And most people would argue that the kernel is, they would not argue that the kernel is the operating system or the key part of it. It's the core. It's the thing that's doing the multitasking and oftentimes the file system and doing the protection and the security. Okay, it's the core. And a lot of what we talk about is going to be about the kernel. Okay? What if we didn't have an operating system? Well, then we take our source code, we compile it, we get object code, turn that into load it on the hardware. Okay, so what's wrong with that? Well, how do you get the object code onto the hardware? Believe it or not, loading the program is a function of the operating system in many cases. Here, how do you print the answer out? Well, that's missing. Here is an Altair 8080. So if you were a hobbyist many, many moons ago, you might buy one of these things as a kit, put it together, and what you don't see here is there are a bunch of switches and a bunch of lights, and this you programmed in machine code, and what you do is you take your program, you translate it into machine code, you print it out, and you'd set all the ones and zeros, and then you'd say first byte, second byte, third byte. Okay? And the way you got output is on the LEDs. Okay, now I don't know about you, but that does not sound fun. Okay? So, believe it or not, the operating system is actually a very useful thing in terms of giving you access to the hardware. Okay? It's giving you an abstraction that's useful. Now, what if you only had one application? So very early computers personal computers ran one application at a time. Okay? Or maybe an embedded controller like an elevator might only run one app. Or remember those 50 to 100 computers in a car? Each one of those might do one thing, like airbags or brakes. Okay? Do they need an operating system? I don't know. That's an interesting question. Maybe in those instances, the OS is less about the protection piece and more about the services it's providing to make it easier for the person designing the airbag app. But here's MS-DOS. Does anybody actually have a computer that runs MS-DOS? Okay, probably not. Oh, somebody in the back does. Good, good. This is interesting because this was the ultimate in simplicity. You actually had some ROM in the BIOS, which actually basic input-output operating system is still on a computer you buy, pretty much. It is a set of really basic routines that are encoded in ROM that tell you how to do input and output and all that stuff. On top of it were some simple device drivers and this thing called command.com, which lets you type commands in, and that was the operating system. Okay, and then your application program went on top of that. Now this is fine and dandy, except there was no protection in here, so if the application program decided to trash something in a device, it could. Okay, it's very easy with this kind of structure to lock the system up and basically get nothing useful out of it. Okay. So what about things like cell phones and Xboxes and PS3s and whatever? Is it enough to have an organization like the MS-DOS one? Do you think I have my new Android phone, which I love, my HTC Evo. Does that run only one app at a time? Okay. How many people have a smartphone of some sort? Okay. More than one app at a time? Yeah, probably, right? So, can you put the OS in the ROM or flash it? Well, yeah, probably, right? Could you get rid of the OS entirely and build it into hardware? Maybe. All right. So, you collectively have been in a world where more than one app at a time is the norm, right? And so basically we need to have full coordination and protection. We have to have interactions between different users or at least different programs. We have multiple things running simultaneously. We have very complex hardware resources. Still have standard libraries out of your OS. And the question you might ask is, here's a bunch of complexity of an operating system that can handle more than one thing at once. Let's go back to the what if I only have one app running? Would it make sense to have this complexity? Okay, how many people think no, doesn't make sense if you have only one app? How many people think yes, it makes sense even with one app? Okay, anybody want to defend that latter position? Yeah.
I mean, you can easily have one app that forks or threads and stuff. It might be that you have one application running, but it's not like it can't have itself divided into.
Okay, great. So today an app means parallelism. Remember, I started the lecture that way. So that would be one reason. Another one which people might have been thinking about is all of the protection that the OS gives you against other apps is actually protection against yourself if you have a buggy app. It means that when your application crashes, you can still get good debug information. You don't lock the whole system up. Okay? So let's briefly, I'm going to close on an idea here. Let's start into the operating system idea here for a moment. What if we want to run multiple apps in such a way that they're protected from one another? Okay, the goal is to keep user programs from crashing the operating system and from crashing each other. And some mechanisms that are going to help, and we're going to make the policy mechanism division quite obvious in many cases this term. One is address translation, and the other is dual mode operation. And a simple policy which we're going to invoke is that programs are not allowed to read or write memory of other programs or the operating system. Okay? So stay with me for a second. Very simple policy, right? The way I get protection is I am not allowed to read or write the memory of either other programs or the operating system. I'm going to make a little virtual container. Okay? Now, what's address translation? Well, basically the idea of address space is it's a set of addresses that a program reads and writes. We'll talk a lot more about this in a moment. And address translation takes the addresses the program's reading and writing, translates them into other addresses. Okay, stay with me. What does that look like? Well, here's a spaghetti diagram that shows you two programs, program number 1 and program number 2. And program 1 has its address spaces, which is being translated to spots in physical DRAM, and program 2 is translated to different spots in physical DRAM. And notice how, because of the translation, these spots don't overlap. So the physical DRAM in the middle is not going to serve as a conduit for program 1 to screw up program 2, because program 1 can't even overwrite program 2 or do anything to program 2. Okay? So this is a good example of the kind of mechanisms in hardware we'll talk about and the kind of OS policies that we'll invoke in order to protect. Okay? Questions? Good. So we're out of time, but we'll talk about some of these later. So here we go. Hold on. So why do we want to study operating systems? One, we want to learn how to build complex systems. And an operating system is a really complex system, so it's a great way to start. We want to learn about engineering issues like why is the web so slow sometimes, etc. You guys hopefully will have a much better idea on some of these. When you go to buy computers or understand the specs, you'll have a much better idea what they mean. And you might actually have business things you could understand. But bottom line, in conclusion, oh, by the way, we'll also talk about security and viruses and stuff. So in conclusion, operating systems give a virtual machine abstraction to handle diverse hardware. Operating systems coordinate resources and protect users from one another. Operating systems simplify applications. Okay? Operating systems give you fault containment, fault tolerance, fault recovery, okay, protection. And finally, CS162 combines all sorts of things from other parts of computer science, languages, data structures, hardware, algorithms. We'll touch on all of those because we got to use them. The end.